let me share. Sorry, forgetting to share. Okay, we're going to talk about direct sums and products of groups. We're going to start with external sums and products, and then we will go to, which are easy, and then we'll go to a little bit about infinite sums and products, because that's an interesting topic for a couple of cases. And then we'll look at internal direct products. That's a little bit more difficult. The abelian case is easy. The general case is a little bit more difficult. Then we have to consider kind of arbitrary products a little bit. And so where do I do that? Yeah, so I'll talk a little bit about semi-direct products. And there are more products. Okay, so there are Reith products. There's all sorts of products of groups. So it's actually an interesting topic in groups. In some fields, it's not an interesting topic. In some fields, it's just really easy. Like cross products of sets are just really simple, or products of sets. But in other cases, it's an interesting topic. So groups is one of those cases. To start off, we'll talk about external sums and products. So the setting here is we have a group G, okay, and I'm going to have all this decoration associated with it. So we're going to have G, we're going to have dot G, and we're going to have EG, okay, and we'll have H, and we'll have that as H. We'll have its operation, multiplication of H, or maybe we also could do the additive. I mean, could be additive, could be multiplicative. I'm just going to use the dot. And in fact, I'll just set the letters next to each other when it doesn't cause confusion. We're going to define a product, GH. Okay, and so this is going to be, as a set, it's going to be the cross product of that set. Okay, and then it's going to have an identity, which is it's going to have an operation, which is the operation of G cross H. And then it will have an identity of G cross H. Okay, and what are these things going to be? So dot G, let's do it like this, okay? So GH, that's an element of there, dot G, or times G cross H, G prime H prime is going to be just what you get when you do the product component wise, right? So G and then a product of G, and then H and a product with H. Okay, so it's component wise product, right? So sort of as simple as you can get. And then the E of G cross H is also as simple as you can get. So it's going to be EG, EH. Okay. So that's two groups. We could do the same with mini groups, right? And so I do point that out in the notes. We could have, let's see down here, we could have, what I talk about? Yeah, lots of groups, right? We could take the cross product of n groups. We could do that using this definition and induction, or we could just, define it basically the same way, where multiplication is component-wise multiplication. Okay, so that's all. And that's it, right? So that's actually pretty simple. Now, maybe we're going to show some properties, in your exercises or something, like if G and H are abelian, then G cross H are abelian, things like that. The one really important fact is for arbitrary G and H, non-abelian, whatever sort of groups, we're going to have this important fact. And that is, we build G cross H, sorry, we build, what am I saying here? So here I'm going to build G equals H cross K, right? So I've got two subgroups, H and K, and I'm building H cross K. So one really important thing here is that if I set, there's the natural copy of H in here, right? Which would be the set of all H, EK, right? For H and H, right? So there's a copy of H sitting right in there, right? And there would be, K hat, right? Would be, EH, K, for K and K, right? So it's just the obvious copies where we take the sort of left-hand things for H together with the identity, and the right-hand things together with the identity for H, right? And then when we look at internal products in a minute, right, we'll see that G is the internal product of H hat to K hat. But really important here is that this is also the same as K hat, H hat. And this is what causes some of the problems when we're in the non-abelian case below, right? So why is that? That's because if I take something, an H hat, so it's going to be, H EK, right? And I multiply it by EH K, something in K hat, right? Well, when I actually do that, right, what I get is H, EH, and then E, K, K, E, K, K, right? But this is just, HK, right? And we could flip that around and we could say, well, this is the same as EH, H, KEK, right? And so that's the same then as EHK times, and notice I'm even dropping the subscripting here of some of this stuff. For the E and for the E's, I'm keeping it for a second, right? And so that's the same as that, and then HEK, right? Otherwise, this kind of would look strange. Right, and so here I've got these multiplied in that order. Here I've got these multiplied in that order. So it's not saying that the group G itself commutes, right? But it is saying that elements of H commute with elements of K, right? In some natural sense, okay? So when we look at internal products later on, right, one of the facts that an internal product is going to have to satisfy is it's going to have to satisfy the commutativity of things between H and K, right? Another thing is this, and that is that H, hat intersect K hat, right, is exactly the single element EH, EK, right? That's the only thing in that thing, right? So that is just the identity, of G, right? Because G is the product group, right? Okay, so that's one important thing, right? And so keep that in mind. These two, if you take the natural copy of these two things, right, inside of this product group G, they commute in this natural sense, okay? Let's see, another important result here is that so now I'm going to go to the case where I get more products, right? So if G1 through Gn, right, is an element of pi I equals 1 to n of Gi. So that's a fancy way of writing G1 cross G2 cross Gn. All right, then the order, so the order of this element, G1, G2, etc., right, will be exactly equal to the LCM of each one of those things, right? So the LCM of G1, G2, right, etc. Gn, right? So you have to look at all those different orders, right? Take the LCM of all those things. And that's because when we look at the powers, right? G1, Gn to the K, right, is just G1 to the K, Gn to the K, right? And the only way this is going to be the identity, which is just E1 through En, right, is if, K is simultaneously divisible by, let me just say it like that, right? If the order of Gi, right, divides K for all I. So clearly K needs to be the least common multiple, right, in order for that to be true. Good. Okay. So I mean, and it also gives us a way of computing, groups, right? So in particular, right, in this case where Gi is a, so this is my Gi. So to just make sure we understand this. So Gi is a cyclic group generated by Gi, right? Whoops, I didn't need that on both sides, did I? And I'm going to take G to be the product, G1 cross cross Gn, like that, right? And we might ask, well, what is generated by the element, which is just, let's call it G equals G1 through Gn. So individually, these each generate, their corresponding groups, right? Well, the only time we're going to get that this generates all of G, right? So G equals G if and only if, right? The LCM of all these things, G1, the orders of all these groups. In fact, I'll write this in two ways, right? So that's the order of the element, right? But that's also if and only if the LCM of G1, the whole, because this is just the cyclic group, right? Up through Gn, right? Has equals what? So equals, well, the size of this product, which is just the product of all these things, right? So let's say that the size of G, just so I can write something, is, so it's, the size of G1, size of G2, up to the size of Gn, right? So let me just call that n, right? Maybe I call this n1 through n. Oh, n is bad. M, right? Let me call this m1, maybe up through mn, right? Like that. Okay, so we have the product of all these is m. So this would have to be the product of all those things, right? M. So in particular, if and only if there's no common factor, right, among the GCD of all these things is just the product of all these. So so all these are like mutually relatively prime, right? So these are mutually relatively prime, right? So we do get, like, I mean, just as a corollary, right? We have Z M1 cross Z M2 is equal to the cyclic group Z M1 M2, right? If and only if the GCD of M1 M2 is equal to 1, right? So that's sort of the situation we're in, right? So we need those to be mutually relatively prime in order for that to happen. Okay, so that's just, I mean, in some sense, we have stronger things in this by the Chinese remainder theorem, but for cyclic groups, right, we're sort of getting this for free. Okay. I mean, so yeah, I mean, so for example, if I have P1, M1, right, this is prime, right, raised to the power, PK, MK, whoops, MK, right, raised to powers, right, where these are distinct primes, and this is some n, right, which is the product of powers of primes, which every n is, then this is isomorphic to Z P1 M1 cross dot 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 cross Z PK MK. Okay. I guess we haven't actually done I mean, in some sense, we'd need the internal products first, but it's kind of, this is cyclic group stuff, right? So it's kind of, in some sense, clearer than the general case. Good. All right. So take a breath there. A little bit about infinite products. So infinite products are just the same. So if I could take some groups, G1 cross G2 cross da 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 da, but you went on forever, right? So now we get this sort of infinite thing, G1, G2, forever, right? So this is, you can think of this as a function, right? From 1, 2, 3, 4 into the set here. More generally, right, I can talk about pi in any index set, GI, right? And so this is first that we'll do the, I mean, in the set theory thing, we sort of talked about this. So this is the set of all F going from I to the union of all these guys, where Fi is in GI, right? So that's a way of sort of generalizing what it means to be a sequence, okay? So that's the product set, right? So the product group, this is an infinite product group, is the group, sorry, where you have the product set in IGI. All right, and then you have this times, so let's just call, I'm just going to call this G, so I don't have to write too many symbols here. G, you have E, G, right? So what are these going to be? We're going to have, so what are the elements of this? What are these functions, right? So F dot G F prime. Well, what do we need to define? We need to define how it behaves on an index, right? At I is F I times and Gi F prime I, right? So again, it's just component wise, but where there's, I many components, whatever this index set I is. And then EG, right, is just going to be the function, right? So that EGI is EGI, right? Okay, so it's really exactly the same definition as before, just sort of boosted up to the infinite case. So that's an infinite product. An infinite sum, okay, so there's sum GI, I and I. This is a subgroup of this. So in some sense, the multiplication, the identity, right, is sort of inherited from this thing here. But what we have in here is G is in this thing if and only if the set of all I such that GI does not equal the identity, right? EGI, right? So they're all the identity except for a finite number. Let me see. Let me not do this notation. Let's just say is finite. Okay. So so the only places, the only indices where this is not the identity element is just is a finite set, right? So really, when we're doing like a sum of these things, in some sense, it's only a finite sum, right? So it's almost like G is sort of like a finite sum with just over those indexes, right? And everything else is just, well, I say sum. Well, okay, I'm saying sum because this is written as a sum, but it's a finite product, right? Where almost everything's one, so those just sort of don't matter. So you just multiply those finitely many things together, and that makes completely good sense. I mean, maybe this will make more sense when we do the internal case, right? But anyway, this is the definition. So we don't get into this much, but you can view the reals, for example, as infinite sequences of zeros and ones, right? At least you can certainly view like the interval 0, 1. Maybe better to say infinite sequences of 0 through 9, right? So remember, this is sort of like the product I and the natural numbers of 0 through 9. You can just think of those as the digits where you have 0 point something 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 something. Now there is a little bit of duplications, like you guys know that 0.999999 is the same as 1, right? So there's some duplication in there. Whereas the rationals intersect this thing would be basically the same set, but where we're doing the sum, where almost all of the things are 0, right? So you have finite decimal representation, or you have infinite repetition, right? So, but basically it would be like the sum over n of the same, these are just like the digits you're using, right? And you could do this in any base, okay? I mean, base 10 is obviously the one we think about, but, sort of take this as an analogy, right? So, the sums are kind of like building the rationals. This product is kind of like building the reals or something. So quite different. Anyway, there's a couple of interesting examples here. So we can take the multiplicative group of Q without 0, right? And we can identify it with Z2 cross the sum over primes of copies of Z, right? And each entry in this copy will give us like, NP for P of prime will give us P to the NP. And now it could be positive or negative, right? So we'll get that a sequence of integers, right? Plus or minus integers over primes. Now, we're in sum, so almost all of these integers are 0. So P to the 0 is just 1, right? So most of those things in the product are just 1, right? So this will just turn into a product where almost everything's 1. So those just disappear. And you just have a finite product, right, of powers of primes. And any finite product, and you're allowing negative powers, right? So you can build the rationals that way. And then you have the plus or minus in front. That's where the Z2 is coming from. So you get plus or minus, you get all the rationals there, right? And so here's an example. So here's like, if I'm looking at primes, this would be 2, yeah, let's see, what am I doing? Maybe this example is not quite right, right? What am I doing? Let's see. I want to go on primes. So the primes would be 2, 3, no, 5, 7. So sorry, there should be 7 squared. What's the next one? 7, 9, 11, right? 11 to the minus 3, so 11 to 3 down there. So I need to change that to a square up there. And then 11, 13, 17, right? So this should be 17 to the 1. So I've got the 2 and the 1 screwed up there, right? And then 23 to the minus 1, right? So that's what this, and then all the rest are supposed to be zeros, right? So that's what that's supposed to be. So there's a way of representing the rationals under multiplication by this infinite sum of groups, right? Here's another interesting one, a little harder to understand, but we can get that the set of roots of unity. So those are those are things like this: e to the m over n I times 2 pi, right? So the nth root of unity would be e to the I 2 pi over n. That's the primitive nth root of unity, and then for m 0 less than or equal to m less than n would be giving all the rest of those things. So that's sort of what those guys are, right? Well, those are actually isomorphic to, so if I call the roots of unity u, that's isomorphic to q sort of mod z, right? So if you think about this, it's like I'm taking a rational and mapping it into some integer part plus a rational part, where this irrational part here is between 0 and 1. So we're like taking a mod 1 over the rationals, right? So s would be less than 1 like this, right? Sort of like, r maps to r mod 1, where now you have to think about what that means for rationals, right? So it's an interesting sort of idea. We're taking q, right, and kind of wrapping it around the circle over and over. That's kind of what this is doing. And then we can take any number in there and break it up this way. This actually uses the Chinese remainder theorem. So m over n, m is something less than n, right, between 0 and n, right? So this could be 0, right, or it could be up to n minus 1, right? We're not quite reaching 1. And then we're going to take that m and here the n here is a product of primes, right? We're going to take the m and split it up using m mod p to the k1 for each piece, and we multiply this back together, we'll get exactly m over n. That's actually part of the Chinese remainder theorem. That's because Zn, right? So m is in Zn, and so m maps over here uniquely to what? Well, it maps to m mod, p1, and again, yeah, this should be p1 to the k1. So this is not quite right, and this should be pk to the what do they call it? PL to the KL, right? So a little bit of typos right there. Actually, this would be a good time. Let me see. Gosh, where is the? Let me pause the recording. Let's see. That's not what I want to do. Keep the screen sharing going. Let me. Okay, so I fixed those little typos there and the little typo there. Good. All right. The next part of this will be internal direct products. So this is it for external direct products. Think about the two infinite cases. They're kind of cute. So the point is we're sort of taking the rationals mod 1 and sort of relating it to this group here, which is kind of fun. Well, not to this group here, but the sum over all these things. Okay. Okay, so internal direct products are where we're taking a group and we're taking subgroups of that group and trying to rebuild the group out of it, right? So it's a slightly different kind of thing. We're working inside a single group. So we've got H and K, which are subgroups of G. We're going to have, so if G is abelian, right, then HK is equal to KH because, the things commute, so that's always going to be true. And so HK is always going to be a subgroup of G. Okay, so that's easy enough. It'll only be the case that HK as those set of products is isomorphic to H cross K if H intersect K is just the identity element of G, right? So now we've got that G living on the outside. And it is clear that HK is isomorphic to, H times, this maybe the notation is bad. So this is actually H times K, the external product, modulo N, where N is the subgroup of just H minus 1. This is because if I take phi, right, going from H cross K to HK in the obvious way, where HK is just mapped to the product HK, First of all, it's a homomorphism that's easy to check, right? And it's clearly onto, right? Because everything in HK comes from something like that. And you just check the kernel, right? So we have HK is equal to E. These things are going to be in the kernel, right? I mean, it's these pairs, right? This pair is going to be in the kernel if HK is equal to E, but that means K is equal to H inverse, right? So that's where I got this this HH inverse thing up there, right? So we get an isomorphism, right? So this thing here, the map going from pairs HK to HK will be an isomorphism precisely when, now this is for abelian, right? Precisely when H intersect K is just the single identity element. Okay, so it's kind of the easy case. Now, we've got a lot of stuff going on, like this n is automatically normal, all sorts of things. H and K are automatically commuting. Remember, this had to be a property of the external products, right? Now, often when we're dealing with abelian groups, we have additive notation instead of multiplicative notation, right? And so here we would have that H plus K would be the set of all H plus K, where H is in H and K is in K. The size of H plus K is equal to HK over H intersect K. Same kind of thing I had before, right? I'm actually repeating what I had up here just with the plus notation. And so we'd have this isomorphism in the case that H intersect K is just the identity element. We have this isomorphism between H cross K and H plus K, right? And that's when we say that we have a direct sum like this. And here I'm probably deviating from the way the book does it. So I'm sort of agreeing with the way that the linear algebra book did last when you took 512. So the direct sum of two vector spaces, right, that are sitting inside of a third vector space, right? That's kind of what this meant, is that I would have two vector spaces sitting inside of some other vector space, and their intersection is just the identity element, right? Then the sum here would be called the direct sum. And that was really important. I mean, in linear algebra, we took vector spaces and broke them up into direct sums and used that for all sorts of things, right? So this was an important concept. Good. Okay. So those are the easy cases. So the external products are easy. Internal products of the abelian case are easy. And now we get to the case where you have to think some. So the general case is that we have two groups sitting inside a group. We're still looking at internal products, right? And we're looking at this map, HK goes to HK. I mean, maybe there's another map we want to look at, but this is the one we're looking at right now. HK goes to HK. And we would like it to be an isomorphism between H cross K and G, right? So we need to think, what has to happen in order for this to be the case. And more generally, we might have a G, and we have several subgroups. And we want G to be H1 times H2 times HK, etc. Right? So one thing you want to have happen here, if we want to say that G is this product, right? So that's sort of the setting I'm in now. When is G actually equal to that product? At least that's what I'm sort of considering here. Well, one thing you want to have happen is that it is, in fact, as a set equal to this product, right? So we want G to actually be equal to that product, right? But then we want this map, H1 through HK maps to this product, to be first a homomorphism and then an isomorphism, right? So we need something going on in order to get this, right? And really important is that, just as we mentioned above, this H and K, if it's going to be equivalent to an external product, H times K has to be K times H. Well, there's no reason inside a G that would be true if it's not abelian, right? So that's something we need to have happen if it's going to be isomorphic to a direct product, right? So you can see it's kind of the problems coming up, right? If G is going to be the direct product of these K groups, then we need all of those groups, not elements of the group specifically, but we need those groups. I mean, we need elements from H1 to commute with elements from HI, right? Things like that. But we don't need them. We don't need all the elements of the group themselves to commute. We just need things to commute between these subgroups, right? So that's a slightly different thing. Let's see. So if we're going to have that G, which is HK, so let me just sort of spell this out a little bit. I haven't written anything in a while, so let me go back to writing. Let me get this back to just viewing. Let me clear this out. Okay, let's see. Let me get this back to viewing only. So I'm in this general case, right? So just to make sure we're clear. So I've got G, I've got H and K, which are subgroups of G, right? and we have that G is equal to HK, and this is equal to KH. So we actually need both those things to happen, okay? And we have G, oops, not G, H intersect K, right, is equal to singleton E, just the identity element, right? So in that case, right, then the map, which is going from HK to HK, right, is an isomorphism. Fism. Oh, isomorphism of what? So over here I've got G. So I keep writing G. H cross K. Over here I've got H cross K, right? And over here I've got HK, right? So we have that isomorphism. We just call it phi. So phi is an isomorphism, right? The kernel of phi is clearly equal to the intersect H intersect, dang it, H intersect K, right? So let's see, why is that actually, yeah, why is that true? So phi of, HK, well, I mean, sorry, in order for this to be an isomorphism, yeah, let's see, okay, two things. Yeah, so what is the kernel? Let's just check this out, right? So the kernel of phi equals the set of all HK, such that HK equals E, right? So it's like that. Okay, so just as before, it's the set of all, let's say H. So it's kind of, equivalent to the set of all H, such that H is an H intersect K. Because this is really the set of all H inverse, right, from this, right, such that H is an H intersect K. Right. So ker phi equals E, the identity element's trivial, right? If and only if H intersect K is the identity element. Right. So that's what we want for this to be one-to-one, right? It's obviously it's automatically onto, right? And it is a homomorphism. The fact that it's a homomorphism that works actually uses, the fact that these things commute, right? So you have to argue that. Good. So that's how you check that something is an internal direct product. You have to check that there is actually an isomorphism. So instead of checking that there's an isomorphism, you can just check that these things happen. That G is equal to HK, H intersect K is equal to E, and HK equals KH for all H in there, right? Same kind of thing for multiple copies, right? We would need to see that G is equal to this product. If I take the product of these things and intersect with that thing, I just get the identity, right? We would need to see that if we permute, right, 1 through m, we permute those things, right, that thing, those are equal, right? So we need that kind of permutation. It's not really, right, it's not full commutativity, right? It's just commuting between elements of these different subgroups, right? And I guess here's a more full-blown proof, right? And I guess I've already talked about the fact that ZPQ is isomorphic to ZPQ when P and Q are relatively prime. Okay. Let's see. Oh yeah, I guess I have one more. Like if M and N are relatively prime, UMN is isomorphic to UM cross UN, right? And so we can define this. Now, this is actually part of the Chinese remainder theorem. So I'm not going to go through the whole proof here. I'll let you sort of look at it. But this is just the map from the Chinese remainder theorem, right? So I'll let you see that it's one-to-one onto. I think actually you had this as a homework problem in the first week of the class. You had something equivalent to this as the homework problem. Good. And there's a little bit of information about the U groups. So this is all in your text in these sections. One last little thing is we can't have groups which are actually look like products. And so an obvious example is the DNs, right? So if we take the DNs and we look at, we've already seen, right, that this can be written as E, R, through Rn minus 1. And then I can have, I can have F, and then I can have RF and et cetera up to Rn minus 1F, right? And that's the entire listing of DN, right? So we see exactly that DN as products, right, is equal to R, the subgroup R, and then the subgroup F, right? So I get those two subgroups there. And it turns out, right, that so this group, right, has size 2, right? So that dn r, now this is from an earlier theorem, is 2, right? So we know that R is a normal subgroup and dn, right? So we're in a situation like that, but we're not in a situation where these things commute with each other, right? So dn is not isomorphic to R cross F as groups, right? It is not true, right? So this is a good example where that's not true, okay? But we can do something, like can we write, so if I take two things in here, is there a way of defining an algebraic, way of doing this? If I do RF and then times R prime F prime, right? Okay, is there some way to write that as some RF type thing, right? And the trick here is that R is normal here, right? So the group generated by R is normal. So I can write this guy here is R. And then I can do this. I can put in R prime. Let's see, how do I want to do this? Oh yeah, I want to do R prime and then R prime minus 1 F R prime F prime, like that, right? So I can do that. So I can view this here as R prime, and this over here is R prime minus 1 F R prime. Now notice that this is a conjugate of F by R prime. So this is an element of, oh, you know what? Sorry, I've got this backwards. Let me back up. I want to squeeze R between F's is what I want to do. Sorry. So I'm going to have R, and then I'm going to have R. Let's see, how do I want to do this? R. Sorry, let me pause for a second. Let me remember what I'm supposed to be doing here. Oh, I can never pause this fast enough. Okay. Okay, it was staring me in the face. I was just missing it. So I want R. And then I want, I just wrote it, I've forgotten it again. Let's see. Oh yeah. I keep, for some reason, this direction is harder for me. It's okay, F, then I want R prime. Now I want F inverse, so I'm going to throw that in there. And then F, so I haven't really thrown anything in there, that's just E, right? And then F prime, right? So the point is I can think of this as R and then F, R prime, F inverse, right? And then F, F prime. And the point is this thing here is in this group. Now that group only has 2 elements, so maybe this kind of seems silly, right? But this thing here is in R because we're normal, right? This thing here is in R because we're conjugating something in R by something in F, right? So that's back in R because that's normality, right? So we had that this was a normal group, right? So this combination here is written as RF this way, right? And so the way we would write this, and I'm not going to go completely into this. We might take this thing and define something RF. So I want to do it like this as the semi-direct product of R prime F prime. Okay, now there's a lot more to say about this, but it does turn out that all DNs are isomorphic to their R group semi-product with their F group, right? So anyway, analyze that in the notes, and I analyze groups of order PQ. So sorry, if G has order PQ, where these are prime, right? And I think the way I have it here is Q is less than P. Then let's see. So we're going to get a subgroup of size. So we get a group, I'll call it Q, right? Is a subgroup of G, and P is a subgroup of G, right? And GP has size Q. So that's the smallest prime dividing the size of G. So we know, in fact, that P is normal, right? So I'm getting this confused. All right, second guessing myself, but right, because if the index of a subgroup is the smallest prime dividing the group G, then P is normal, right? So we get P is normal in G. We can see that G as a set is equal to, I want to do it in this direction, I guess, PQ, right? Because the elements of this, given the fact these are prime, there will be P times Q many elements of this. There's P times Q many elements of G, right? So these have to be the same as sets, right? But in general, if G is not commutative, right, then G doesn't have. So one case is it might be that G is commutative, and if G is commutative, will imply that G is isomorphic to just ZPQ, right? If G is not commutative, then G will be isomorphic to P Q, right, the semi-direct product. And what I don't do actually in the notes is kind of analyze what's actually going on here. I just sort of get some different semi-direct products and say it can be one of those things, but actually I think those are all the same. Maybe I'll add that to the notes later, but anyway, there is this different notion of product. It isn't too hard to see how it works, but it does start becoming more complicated to apply it. And then there are groups that are not semi-direct products. So the quaternion group, if you want to, this is in your text and it's other places. This is not the semi-direct product of any of its subspaces. So there are groups that are not direct products. There are groups that are not semi-direct products. Now maybe Q8 is some other kind of product, right? So there are other kinds of products. So it is a big area of group theory, but this is already more than you actually need to know. I just wanted to show you the semi-direct products and show you that Dn, at least, can always be sort of written as this nice semi-direct product. And I will stop there.